right down and not the left. Could I have drawn it to the left? I could draw whichever way I want. This is the part of the class where we don't necessarily know which way forces are going, right? So you just draw it any way you want. I have a tendency to just draw it in the positive. And then if I drew it in the wrong way, what happens?
You have a negative.
I get a negative later. Okay, so we have A, B, C. So Jabin, we're up to you. What should we draw in here?
The tensions
Okay, the tensions, and how should I draw them?
B going up into the right.
Up to the right,
It's the same as C going up to the left.
right. And should they both be called T?
Sure.
Why?
Because of the pulley.
It's the same cable. It's a continuous cable going through the pulley. Let's put down they give us the angles, right?
Yes.
Okay, Claire, what else should I draw?
Draw P.
P?
Definitely.
Okay, and they didn't give us a distance, so we can't put a distance. Aaron, what else do we need to draw?
Reactions at support A.
Reactions that support A. And what kind of support is it?
Looks like a, what do you call that? A pin? I know
It's a pin again. So what do I draw?
Forces in X and Y, and you're going to have a...
Force in the X and force in the Y.
Z.
And I think what I'm going to start doing, everybody look up here, is I'm going to call it AY and AX. Just so that we know that, because there are going to be cases, could you imagine in engineering, we're going to have more than one connection on something, right?
Probably.
Right? So let's start calling them by their location, AX and AY. Aaron?
So because that's going to resist the X and the Y in both directions, it doesn't matter what direction you draw our
It
forces.
doesn't matter how I draw AX and AY, I just draw it one way.
Cool.
I find that for me, it's better to be consistent. I make less errors, so I usually draw them positive. Okay, you feeling better on this one than in the last one? Okay, next one. 13. This is a big one. They want you to draw a free body diagram of the bars and a free body diagram of the cylinder. And this is very much like what we did way back at the beginning of the course. We kind of did this problem already in a way. Let's draw it on the other side. Actually, we don't need two screens.
Joanne,
Yeah,
with problems like these, are we always going to want to separate every piece that's connected?
it depends, and we'll do problems like this. Remember that we did one problem where we kept things together. We have to decide, we're going to go back to the same process. How many unknowns are there? How many equations do we need? How many free body diagrams do we
And the
need?
reactions of that pen. No. Why?
So these aren't free body diagrams.
They're all free body diagrams. Yeah.
So you have draw, like if you're, you have to isolate a point, and now we're drawing multiple points, so it
Yeah,
seems like.
okay, yeah, so let's talk about that. So I just got a question, are these still considered free body diagrams? Because we're used to drawing free body diagrams where it's just a point, right? And then all these forces coming off a point. But when we started in statics, we were dealing only with a body that has concurrent forces on it, right? When all the forces come to the same point, a free body diagram was only a point. Well, now we're dealing with forces that aren't all acting at the same point. So our bodies are truly bodies now. You know? So our free body diagrams are drawings of bodies. Okay, so Uriah, we're up to you. Let's look at DCB. Do you guys need another minute for this? Okay, 1 minute.
Yeah, the normal.
There's the normal there,
Yeah, and then yeah.
So we're ignoring weight, right? We're only drawing normals, and normals are compressive forces.
normal.
So if you and I are touching each other, and we want to draw a free body diagram of you, we're going to draw a force going
I'm
that
not
way.
sure
If we're going to draw a free body diagram of me, we're going to have a force going towards me. Because first, we're touching each other. And as soon as I remove, you have to know what it felt like to have me there. So it was a push.
So you would draw on the bar and the ball, because they're two separate.
Right, when you separate them, you have to account.
Well, either way.
Okay, Uriah, for DCB, what do we need to draw on it?
There's a normal force in between D and C.
The normal force between,
D and C.
okay, tell me what's the normal force created from?
From the cylinder.
From the cylinder. So on BCD, you guys, everybody look up here. We had a cylinder here. I put a little dot where it was. It's probably lower, but it's probably lower, right? That doesn't matter. So if they give us the distance, then it would matter. But we have this ball, the cylinder here. Once we remove the cylinder, we have to account for it. So which way do I draw the force?
Going, let's see, DCB, it'll be going up and to the right.
So we're drawing this bar, right? And this force is leaning on that bar, right? So the cylinder is creating a force on DCB. How is that force directed?
Okay, it would be
Down to the left. Thank you. Does everybody agree? Because what is that bar experiencing? It's experiencing a push from the cylinder. So it's got to go down. Should we call it just normal 1?
Sure.
Okay. Eric, what else do we have on DCB?
The tension going towards the left on.
Going towards the left. And is this correct that the tension should go towards the left? Does everybody agree with that?
Yes.
Okay, what else? Enrique?
DCB,
On DCB, yeah.
there's reaction at point C.
Right.
In y in x direction.
Okay, and what do you think the connection is?
Connection is a pin.
It's a pin again. So there's got to be an x and a y. So CX, right? We're going to start getting into a habit of calling it CX, whatever the point is, CX and CY. So does everyone agree that when you take this bar, DCB, out, we have to remember that it experienced the cable, a tension, it experienced the compression, a normal from the cylinder, and it experienced something, the reactions of support from the other bar. Santiago?
Would it be wrong to give the direction of the normal going out to the right?
Yes, it would be wrong. So explain why. If we had the normal going this way, that's not how it experiences it, right? right? The cylinder is pushing on this. The normal, like here, if you have a box, you guys are all comfortable. Here's a box, and here's the surface. Which way do I draw the normal? If I'm drawing a free body diagram of the box, how do I draw the normal? Up. Does everybody agree with that? Everybody agrees, right? Why?
Because the box is experiencing that.
Because the ground is pushing up. If it wasn't pushing up, the box would have went right through. It would have been quicksand, right? So the ground is pushing up to keep it up, right? Otherwise the box would have dropped. So I think sometimes you guys, because you do simpler problems in physics, you think, oh, here's the weight, and the weight and the normal are just opposite, so I always draw the normal opposite the weight. Well, that's not the case, right? We draw the normal in the direction where the push is occurring. This bar is experiencing a push, a normal from the cylinder. The cylinder is pushing on it. It's got to be perpendicular, going down to the left. Okay? And I want you to know that. I don't want you to draw normals in the wrong direction and then to get negatives, because you need to understand the way of a normal. So there are three forces, hang on Chelsea, there are three forces. I want you to draw them correctly. Weight. We always draw weight down, right?
Yes.
We always draw tension away from the body because it's a pull. And we always draw normals towards the body because it's compression. So those three forces you have to have drawn in the right direction. All the rest, we have no idea. CX and CY, I don't know, maybe they're going the other way. Okay, Chelsea.
So if the cylinder had weight, if it had some kind of value of weight, then what would we do differently on that?
Nothing. The only thing we would do is draw a weight on the cylinder.
Okay.
Would we draw a normal at B between the contact of the
Yeah, so we're not finished yet.
Oh,
We still have one more thing. Yeah, good. Why don't you take it? Why don't you do it?
me? Okay.
Okay, what's the other thing we need to put on this?
Normal at B.
The normal at B. What do you want to call it? N sub B. Does everybody agree? Because when you take this bar away from everything, it experienced the normal down here. Good. Lucas, wake up.
Thank you, guys.
Jose, question?
Yeah, is it okay if you put the normal on the starting the tail at point B, going up? Or
Yeah, you can draw it like this. If you want to draw it like this,
Yeah,
yeah, that's fine. Just draw one of them.
okay. Cool. Awesome.
I'm going to keep it like this though.
That's fine.
But you can draw it like that if you want. Okay, let's do ACE. Lucas, what do I have to draw in ACE?
Similar to the previous drawing.
Okay.
Mirrored over. So,
Do the forces.
tension off of A,
Okay, which way, left or right?
right,
I like that answer.
What else?
and then normal for A.
Which way?
Down, or I'm sorry, up.
Up.
And CX.
And how should I draw CX and CY?
I think that CX is gonna go that way.
It's got to be opposite. This is, what's that law, equal and opposite? Is that the third one? It's got to be like this, because when we put these two guys together, they got to cancel. Okay, what else? Maria, what else do we have to put on here?
Normal form,
Right, which way?
right.
Down to the right, we'll call it what, N2 maybe? Anything else? I think that's it. So if we drew these two together, and this is A, B, C, D, and E. Gradient, what would I draw on here? We did this way back when we were doing statics problems before we got into the moment stuff.
Normal?
Right, which ones?
A, C, down.
Say it again, give me the variable.
N1 and N2.
Okay, N1 and N2, so here is N1, and here's N2. What else?
Normal at B and A.
Right, normal at A and B. What else? Anything else? Oh, I have to, if these guys are connected, there's a cable here, right?
Yeah.
So do I need to draw anything else? Do I need to draw CX and CY? No, because they're connected now. So two ways to think about this. One is when you separate things, you have to account for the forces. When they're together, you don't. The forces are still in there, but they're internal to the system. The other way to think of it is when you put physically these two things together, the CX's cancel and the CY's cancel. So they can't be on this drawing. Bonnie?
So, on that one, you draw the cable instead of putting the tensions?
Yeah, I do the cable, yeah, because I would have drawn it at the beginning, but I kind of forgot. But you put the cables on there because it's all connected still.
Okay.
So I should have drawn all this together initially. And then when the same thing goes, when the cable's cut, you have to account for it, but when it's together, it's in there. Maria?
Since the picture says that there's a weight W, do we have to add that?
Oh, yeah, the cylinder has a weight, good. So we didn't get up to the cylinder yet, so we're good. Okay. Bonnie?
One more thing, you're not drawing the angles in this case, is that, would you normal, or you just kind of?
Well, I put, do they give us the angles and everything?
Yeah.
Yeah, they did, so yeah, we need to do that. So what is it, 40, they're both 45?
That's the null force that's experiencing.
And then it's a free body diagram, so we also have to have an X and Y. Stop.
So if the CX's are going different directions, wouldn't that make it so the X components of the normal forces would both be negative? And they just add to be a larger negative?
No, because we also have tensions. When we do
Okay.
some of the forces in the X, we have to take into account CX, the X component of N1 and T. And in the end, the normal has to be a positive value because it's got to go in that direction.
Okay. Well, I guess
So it
it's
depends on what the
opposite.
magnitude is.
Yeah.
But the normal has to be in that direction. Okay, and now how about the cylinder? Bonnie, we're coming back to you.
The weight going down?
Yeah, so they did tell us we have to draw weight. What else?
The two tensions, the two normals coming in, the angles in the bottom.
Okay, so let's see. This one is touching this one, this is an N2, right?
Yeah.
And was this 45 degrees again? 45? 45. So this is also 45. And then the other one's coming in like this. And does it make sense that the N1 and the N2 are pushing into the ball? Larson, explain why N1 and N2 should be pushing into the ball.
Because the weight is pushing towards.
Forget about the weight. When you describe normals, I know you've been trained to describe it in terms of weight, forget about weight. Just talk about it in terms of the normal, because the normal is created by the surfaces, right? So why do these two normals go up this way?
Because it's touching.
It was touching this bar, and the bar is pushing up on it. So the bar is pushing up on it, normal goes this way, bar is pushing up on it, normal goes that way. It's what it's experiencing, which is a compression force. Okay, let's do the next one.
Do we write that N1 and N2 equal the same and then N and E equal?
Say it again?
Would we write that the normal and normal 1 and normal 2 are equal in magnitude?
In the end, they are equal, and why are they?
Because it's supporting that one ball.
Say it again?
It's supporting the ball. With
And what else? Not just because it's supporting the ball,
same direction.
it's totally, the bars are totally symmetric. right? They're in the same direction. If the bars were like this and they were in different directions, then they would be supporting it differently. But this is totally symmetric. The weight of the, right, the weight of the cylinder has to be uniformly distributed, unless it wasn't.